So the last thing we're going to look at in this unit is something called escape velocity. So how this one works is, so again, from earlier, from last day, we saw that the energy way far away is considered to be 0. So the energy way far out is 0 joules. So we have the following equation. So potential energy is negative Gmm over R. So let's say we're starting somewhere. Let's say we have something, we're starting here, we have some amount of potential energy. And escape velocity is basically if we want to completely leave the gravitational pull of an object. So what this means is that right now we're on Earth, and if we need to find out what speed do we need to travel, such that if we were to leave Earth, like if our speed is smaller than this value we calculate, we would eventually be pulled back around and return to Earth. It's kind of like Halley's Comet. It goes around, or it goes really far out, but every once in a while it comes back and circles around the sun. It is unable to escape the gravitational pull of the sun. So we can actually calculate the velocity to escape any specific massive body in space. So right here, our potential energy is some value. So what we can see is this is the energy before and energy after. So basically, we need to bring our total energy to 0. So we need to somehow get 0 energy. So if we're starting with negative Gmm over R, whatever location, if we add kinetic energy to it, so the potential plus the kinetic, if we can bring that potential energy to 0, that will give us the minimum speed required to get away. So what's going to actually happen if you just have that exact minimum speed? You'd escape the gravitational pull, but then you'd kind of just be stuck there where, oh, there. If you want to keep going, we'd actually need a speed greater than what we're going to calculate. So we can see here. So here's our equation. We're saying we have to bring our potential energy to 0 using kinetic energy. If we rearrange our equation, so for V, we get 1/2 mv squared is equal to Gmm over R. Rearrange our equations, we get this expression at the end. So this is our escape velocity equation. Now you could go ahead and memorize this. However, it is hoped that you can derive this expression on your own. So here's a escape velocity question. It says, what is the escape velocity of a Saturn V rocket trying to leave the Earth? So we just go ahead and use V is equal to the square root of 2Gm over R. The mass of the Saturn V rocket doesn't matter. Of course, if you need more energy, if the rocket itself is bigger, you need more energy to speed up to the required speed. But regardless of the mass, this is how fast it has to go. So just go this. So we're just going to plug in our values. We have 2 times the gravitational constant, 6.67 times 10 to the negative 11. And we're going to multiply that by 5.97, the mass of the Earth, times 10 to the 24 kilograms. And divided by our radius. So if you're already further out in space, it actually needs less energy. But since we're on the surface, we're trying to figure out how much energy is, what speed we need to get to. And we get a value of 1.12 times 10 to the 4 meters per second. Again, because Earth has a atmosphere, there's going to be some frictional forces. Again, this, if we were already out in space, you can get a lot more accurate value. So we'd actually need probably greater speed if we're on Earth, because we have to first overcome the frictional forces of air resistance, etc. So again, just to recap what's happening, here's our planet. We're starting at our Earth. We have some rocket ship that is on Earth with its, and fires out and it wants to get somewhere out here, which is considered to be infinitely far away. So again, delta, the change in potential energy, negative Gmm over R infinity, that's just equal to 0 minus negative Gmm over our Earth. So our change in potential energy is just gmm over the radius of the Earth. So that's how much energy is required.